certain bits to the existing message bit, and if you check bits, then you will have an idea at the receiver that whether there is error, any error in the channel or not. Means, so that means what I like to say at that it means at the end at the transmitter, say I have certain message bits. So say 6 bit of data. Now, or say 3 bit of data. Then what I am going to do, I will append say 3 more bits. Okay, depending on the existing message bit, and the 6 bit I will transmit to the channel. At the receiver, he will just means examine those extra 3 bits that has been appended at the transmitter, and also you have that the received message bit. From this appended and received 3 bits, you will have idea that whether the message bits received are the original message bits or it has undergone certain error. It has suffered from some error. Not due to channel. Please remember, due to channel. Channel noise or something. Okay. So the say here now here we talk will be either you can do odd parity or even parity, but mostly even parity is used. Means even parity means it is say in this example, say this is my message bits. This is my message bit. Okay. Now in this one, you see even parity bit means that number of ones I will this is my parity, even parity. So I will first of all I will break it into number of blocks, number of blocks. Let me say block 1, block 2, block 3, block 4. Now each block, so that means the 2, 4, 5 number of message bits, and 1 bit I will append at the left maybe. It doesn't matter. You can also append this side also. Generally we put either at the either end. Okay. Now, how will we put in that even parity means that number of ones should be in the total number of this means after appending this parity bit, this is called parity bit. After appending this parity bit, this is called the code kind of code bit. Now this code bit, that in the code bit that the even number of ones should be present. That means here already 2 ones are there. So how many ones you need to put to make it even number of ones? 0. Now in this one, in this case, you see there are 3 bits present. So you have to add 1 so that you have 4 number of ones. So that is even number of ones. Similarly, say here, say yes. So here I have only say this is the block. The block size should be 2, 4, 6. The block size should be like this. So I have only one bit. So I have to put another 1 bit so that even number of ones are present. So this is my parity bit. Okay. So this is the even parity bit. Or you can talk about odd parity bit. If you talk about odd parity bit, then what will you do? How many ones you will put here? Then in odd parity bit will be 1. Here already you have 3, so you will put a 0. Now here you have 1, so that means you will put a 0. So it is even parity is the complement of the odd parity bit. Any of the parity bit you can use. If you use even parity bit, the receiver should know that the whole system is using even parity. Okay. So in this case, forget about even parity. Forget about odd parity. Now let me talk about even parity. Okay. Now in this even parity. Now in this even parity, how will you detect the error? That means after say that this one you have sent and say at the say from the transmitter, it has this block has gone through the channel and finally it is received at the receiver. Now during the in the channel, say this particular bit has there is some error and it has changed to 1. Now you see at the receiver you are seeing even parity is used. Already 3 bits are sent, three ones are there, but still there is some. Then if there are 3 ones, then I should expect there is only 1 over here. But my even parity bit is 0. That means there must be some error in this block. There must be some error in this block, but I don't know which block, which particular bit is affected or what, that I don't know. But there isn't 1 bit error. Okay. So similarly, say here there's one. Say this one, say it has got a corruption and it has become 0. Now then already at the receiver, what happened? What will you observe? So there are 2 ones, but here also there is 1. That means there is some problem in this. There is a bit which has undergone some which is received in error. Now, but you see, so we have understood that means 1 bit error detection. 1 bit error detection capability. Error detection capability, not the error correction capability. But the problem is, instead of 1 bit, if there are 2 bits are in error. If there's a 2 bits are in error, okay, then what happened? Say here there is 1 error, so it has become 1, and say this 1 becomes 0. Okay. Then what happened? That already 2 bits you have received. Okay, 2 ones are there. Yes, you are supposed to receive you are supposed to get the parity bit 0. Yes, you are also receiving the parity bit error 0. So that means you see that 2 bits error you cannot detect. If there are 2 bit error, then you cannot detect. 1 bit error you can detect. Okay. Now, say similarly, say if I do here. Say this both 1 has become 0, 2 bits. Okay. Then what happened? That you are getting only 1 at the receiver. Okay. So yes, I must expect that here where 1 is there. So I don't have to. So we will assume that yes, the receive block is correct, but which is actually not the case. It has undergone 2 bits of error. Now again, if you see, if I have a 3 bits of error. Now, if I have 3 bits of error, and I am assuming the error is in the message bit, not in the parity bit. Say 3 bits are error. That means say 0, 1, 0. Now what happened? Then I have even parity. You see that what happened to the even parity? Now how many? This 1 becomes 0, 0 become 1, 1 becomes 0. So then now in the total message, this is, then I should expect there is 1. I should expect that, see, now what is my message bit? 0, 0, 0, 1, 1, 0. So I should expect there must be 1. Okay, but it is 0. That means there is some problem. So that means say 3 bit of error can be detected. So similarly here you see that my message bit is 3 bits of error. Okay. Now what should, now my parity bit is this, But you see that there are 3 ones, but that cannot be in the message bit. How can it be? So it is already 2 ones are there. So that means I should expect over here 0. That means there is 3 bits of error. So that means when you are detecting, that means you can detect 1 bit of error, 3 bit of error, kind of thing, maybe 5 bit of error. Okay, but not the even bit of error. You cannot detect. Okay, and you cannot correct. That is the point. So this is the parity bit. Means parity. Now you see that if I calculate now we can calculate that the undetected error. Okay. Now that the probability of J errors occurring in a block of n symbols. Okay. So that means probability of J errors. That means NCJ p to the power j1 minus p to the power p is the probability that a channel symbol is received in error, a particular channel symbol, any. So NCJ, this is NCJ. Now this is just a binomial distribution. This is binomial. Okay. Now you see that probability of undetected error. So undetected error means then it will be j equal, say for n equal to say even. Okay. So that means probability of undetected error will be j1, j2, j up to n by 2, and say nc 2, nc. That means you see that 2 bits you could not detect. Now you see 4 bit nc4, nc n by 2 kind of. So it is like that nc2 p to the power 2 1 minus then plus nc4 and all this p finally nc n by 2. I am assuming n is even. Okay. Similarly, if n is not even, then n minus 1 by 2. So that means this is the probability of. That means you see that in the previous case that 1 bit we could detect, 2 bit error we could not, 3 bit error we could detect, 4 bit error we could not detect. So that is 2, 4, all these bit they are all undetected one. So when 2 bits are in error, so out of n 2 bits are in error means any 2 bits are, so that means nc2 p to the power 2 1 minus p to the power n minus 2. So similarly nc4 p to the power 4 n minus 1 minus p to the power like that. So that means this is your probability of undetected error for the even parity code. Now see they have taken an example and you see that probability of a channel symbol that will be that receive channel symbol that will be in error. So that means in 1 in say 1000. Okay. This is the probability that means actually from the transmitter you have sent 1 and the receiver due to channel non-ideality you have received 0, or you have sent 0 you have received 1. So this probability, this error probability is 1 by 1000. Now say message bit, if this and we are what we are doing, we are just 3 bits message, we are adding 1 bit parity. So that means k equal to 3 and n equal to 4. So 3 comma 4 or n comma p or k comma n. What is that? N comma k put k by n. Big number is passed. 4 comma 3. Sorry. Okay, it should be 4 comma 3 code. So 0 0 0. So that means your parity should be 0. Even parity I am talking about. Please remember this is even parity. Okay. Now 1 0 0 means I have to put 1. So that means total 2 number of ones are there. 0 1 0 means I will put 1, so that 2 number of things. Double 1 already there, so I will put 0. like that. This is my message bits. So this is my message bits and this is my parity bits. So that this is my code word. This is my code word. Okay. For this message bit, this is my code word. This message bit, this is my code word. Now that the code is capable of detecting all single and triple error patterns, because you have what means this is 4, n equal to 4, so that means probability of undetected error was nc 2 plus nc 4 pnd. Okay, so that is nc2 means p square 1 minus p square, nc4 or that. That means if you do the calculation, then it is something. You see, that means, oh, 6 into 10 to the power minus 6 kind of thing. You may feel, oh, this probability of undetected error is quite small, 6 into 10 to the power minus 6. But you see that what your data rate, if your data rate is something, say 1 Mbps. Okay. Now, if your data rate is, if your channel is some sort of 1 megabit per second, then so that means in 1 second you are sending 10 to the power 6 bits. Now if you send 10 to the power 6 bits, out of 10 to the power 6 bits are in error. Okay. So this is the idea actually. Now say, so this is about this simple parity code kind of. Now let us do about rectangular parity code. Rectangular parity code means, say, what I am doing, say this is, say I have some sort of a message, a long stream of ones and zeros. I am breaking it into rectangular blocks. Okay. Now rectangular blocks, out of rectangular blocks means I am rather breaking it, so something like that. Okay. So this side. Okay. So similarly, okay. Now then, what I am doing in the, so that means this rectangular code, or sometimes we say the product code. Now here what I am doing, I have total message is, say this is, if it is m cross n, this is something, say this is m and this is n, but here m equal to n anyway. So what I am doing, I am putting this column, this column as a parity. Similarly, this row is another parity. That means first what I am doing, how many in this row, let us see, in this row let us see. So already 3 ones are there, I have to make even parity, so I will put 1. Then in this row I have only 1, so I will put 1. So that 2 even number of ones are there. Here already 2 ones are there, even number of, so I will not do anything, 0. Now here odd number of ones are there, I will put 1. Then here I will put like this. So this is my, this I have added up to this. Then what I am doing, I will put a parity on this side. That means, say already in this column I have 3 ones, so I will, odd number of ones I will put 1. In this one I have odd number of 1, I will put 1. In this row, in this column I will put, I have already odd number of ones, I will put 1. Then in this one also I will put 1. In this one I have an even number of 1, so I will put 0. And in this one 2, 4, so I will, so even number of ones are already present, I will put a 0. So this is a parity, that is also parity. Now my block size is n plus 1 into n plus 1. Earlier so that means my coded block was n plus 1 cross n plus 1, but my message block was n cross n. So here n is basically m plus 1 into n plus 1, and what is your k, message bit, as m into okay. Sorry. Now, say m equal to n equal to 5 and they have explained the picture. That means that in this case, the code is, say if m there 2, 4, 5, so that means the code is 36, 25. Now, the question is that why will I use this rectangular code or product code? A good thing of the product code is that you can detect. You can not only detect error, because you can also correct error. Okay, that means you can localize the error. That means, see, how can I detect error? Say in this block. Say I have already 2, 4, 5 number of ones. Say I have here. I have some error. I have a G. Okay. Then what will happen? But my parities are intact. I told that error is only, I am considering error is in message. Say I have an error. Okay. So, but I don't know actually. So what I am doing, I will check. Oh, this is the parity one, but I should. This is already 4 ones are even number of ones are there, but still there is one. That means there is some problem in. There is some error in this. Okay. So similarly, you see here I am seeing that 3 ones are there. So but I should then expect a 1, but I am getting 0. So that means there is some problem in this column. Okay. So that means the intersection of these two, that means here is the problem. So that means what you have received, I have received 0. So no, it should not be 0, it should be 1. Okay. It should be 1, and if I put 1, rest of the things are matched. Okay. So that means it has some 1-bit error correction capability. So and in this one, that means, and similarly that you can calculate certain message error kind of thing. So that please study on your own. It is the same thing. That means it is just so what is the probability of now that such an error? This is an error correcting block code. This is an error correcting block code. But what about the probability of? But still, we compute the probability of the decode for an uncorrected error by accounting all the ways. The probability of uncorrected error I have to calculate. Now, for uncorrected error means that means j equal to p plus 1 to n. Actually, mcj p to the power 1 minus pn minus j. Now, in this case, in our case, you see that means it will start from j equal to 2. Okay, it means t equal to 1 actually. 1 bit we can do the error correction. So that means if I j equal to if there is some 2 bits error, I cannot do the correction. So then you can calculate that 30 means that this is the summation j equal to 2 to 36j pj 1 minus 30 p 36 minus. Now when p is reasonably small, you can drop this summation and you can put this. You can put this value. When p is reasonably small, something around 10 to the 8 or 10 to the 9 kind of. Okay. So this why we put this thing, so that you will have some idea. Otherwise, you have to do all this addition and all these things. Or otherwise, you can do 1 minus the other one. Anyway. So this is the this is the probability of the undetected error. Now the question is that why will I use the error correction code? Now you see that Why will I do the error correction coding? Okay. Now you see that we know these characteristics. These characteristics is the probability of bit error divided by EB by N0. That means it is some sort of a what is this EB by N0? EB by is this a normalized SNR that we know. Because it is the signal power by noise power. EB is the bit energy. EB is the bit energy means EB equal to PB into TB. PB in power, sorry, PB, P into TB. TB means RB. Okay. Now this is N0. N0 is signal power, P noise divided by frequency. You know, Pn by frequency means bandwidth. Okay, so signal power by noise power divided normalized by W by RB. Okay. Now this now if you see that this particular curve is the characteristics of, these are quite important characteristics. This PB versus EB by N0, these characteristics this is for coded one, and this one is for uncoded one. That means if I don't do the channel coding, then I will have this type of characteristics. If I have a channel coding, I will have a better characteristics. Better characteristics means, see, why do you say that it is a better characteristics? That means, say this is my probability of bit error. For probability of bit error, if I use uncoded one, my required signal to noise ratio is this much. Okay, this much means say almost like say 10. It is say 10. Okay, 10 dB. But if I use the coded one, my signal to noise ratio is much less than the 10 dB. When signal to noise ratio less than means I have to pump less power for the transmitter side. So my battery life will increase at the transmitter side. Okay. So means I have to generate the symbols, that means 7 plus symbols, or if you do the baseband communication, so baseband symbols, that I need not pump that much energy to the symbol. That means symbols sin omega t theta or something, that should be okay less so that you can manage with the signal to noise ratio. So always I want, please remember, I want my this card should be in this direction. This is my desire. Okay. So probability of bit error also will be reduced. It is the, see, please remember, this is EB by N0 required. What? Okay. So that means that I have to pump, I have to supply. So I want both the EB by N0 to be this side, also PB should be this. But the characteristics you see, that means if you play with this thing, say if I am at this point, oh, less probability of bit error, but my EB by. Now if you no, you cannot supply this much 14 dB power, 14 dB this signal to noise ratio normalization. So what you have to do? You have to go back. Say you can go up to, I can do up to 9 dB. When you go back this 9 dB, suddenly your probability of bit error has much increased from 10 to the power minus 6 to say 10 to the power minus say 10 to the power minus 3. So probability of bit error. This is the basic idea of this graph. Okay. Now the question is, that means there are certain trade-offs. Trade-off means trade-off error performance versus bandwidth. Say the system does not use the error correction coding. Okay, say and the system is operating the communication system and it has not used the error correction coding. That means it is in these cards. and say it is operating at point A. Point A means somewhere here. Point A means somewhere here. So your probability of better is little high, 10 to the power minus 2, and your 10 to the power minus 2, your probability of better is very high. That means when in 1 Mbps data, 1 Mbps data, you are in 10 to the power minus 2 is the case. So that means 10 to the power 4. That means 10,000 bits are in error. Okay. Is it like this? 1 in 10 to the power minus 2 means each 100 bit 1 error. Okay, so 10 to the power 6 means how much? 10 to the power 6 by 10 to the power 2, 10 to the power 4. That is 10,000 bits are in error in 1 Mbps data. So that means it's a huge error. Now you see that say after a few trials there are complaints about the voice quality. Why? Because you see in 1 Mbps data, if you have some sort of a 10,000 bits are garbled, so there must be a complaint from the customer that your voice quality is not good. Okay, so then that the customer suggests that bit error probability should be lowered to 10 to the power minus 4. So that means he wants my bit error probability should come down to here. Now, if I do this, so in order to get that, so what you have to do, if your bit error probability reduces from the transmitter side, you have to pump more power at the symbol. That means you try to understand. That means say you are from the transmitter, you are sending the sinusoid. Sinusoid is corrupted with noise, and you are receiving the sinusoid. Now but still, if your sinusoid is very small and means dipped in a noise, so then what will happen? You will have error. So then what you have to have? You have to make bigger sinusoid, means big amplitude sinusoid. Then your error, and assuming error is same, then your signal to noise ratio increases. Now bigger sinusoid means you have to pump more power at the transmitter. Pumping more power at the transmitter means your battery life reduces. So that means in that case the required signal to noise ratio that has something here. So it is something like that 10 dB has reached. Okay. Now say that from one thing is that you can go to, if you do the uncoded one, if you are so uncoded on the, if you don't do the channel coding, so you are here, so you have to give a 10 dB ASN. But if you instead of without using channel coding, rather if you use channel coding, that means if I can move down directly here, then I will have this. What will be my probability of means the required SNR? Required SNR is still 8 dB. That is earlier also with the higher probability of error I have 8 SNR. 8 means 8 required EV by N0 was EV by required if normalized SNR was 8 dB. Now also if normalized SNR was 8 dB. So that means I have to change my scheme from uncoded to I have to use the channel. Okay. So that means channel error can be detected, so that my probability of bit error will be much reduced. Okay. Now only thing is that this error is due to probability of undetected errors. Now what is, so that means you are happy. That means so from this one to this one I have reduced. But what is the cost? That means if you do the channel coding, now so you are happy. That means I have managed, because my customer has said to reduce the probability of bit error. I have reduced it, but still I have not increased my power. It's SNR required SNR. So that means my battery life remains unchanged. But what is the trade-off? Trade-off is when you are using channel coding, you are asking for more bandwidth. That means you are sending more data. You are sending more data for a real-time communication. So try to understand. That means say earlier in the real-time communication means say this is your 1 second time. Okay. Earlier you are sending say 1 Mbps kind of 10 to the 6 bit of data. But now you have to, in this 1 second, you have to send some sort of a say 1 bit if you add in each 10 bits. Say. So it will be much more. Say, rather each 100 bit, each 800 bit, you are adding 1 bit. So that means you are adding another 10 to the power 4 So in real time communication, 10 to the power 6 plus 10 to the power 4 bit, that should be in case of real time, you have to put inside this. So you are actually, for that you are asking for more bandwidth, because that why more bandwidth? See, you try to understand. That is earlier, say you do 10 to the power 6 kind of thing, you try to do 10 to the power 6 like that. You are transmitting like say 101010 kind of. It's a baseband dynamics. Now in this whole thing, now you have to do 10 to the power 6 plus 10 to the power 4. Then what you have to do? You have to something like that. You have to do. Sorry. Now, what you have to do? You have to reduce it. Then if you reduce your this thing, if you take the transform, Fourier series and all these things, for means say you are assuming you cannot transmit like this, you have to transmit say this one, maybe fundamental, first harmonic, third harmonic, say seventh harmonic you are sending. That means say you are sending F0, 3F0, 5F0 and 7F0. Okay. Say because after that all the amplitudes will be very small. So if you do the Fourier series of this one, it will be coming like that. So that means some sin 2 pi F0t, then sin 2 pi 3F0t, sin 2 pi 5F0t, 7 up to infinity, all infinity kind of thing, as it is a square root kind of thing. Say, but after 7th harmonic, you have seen that this is very small, so it's okay to discard. So that means, but now you see that in this case your F0 is reduced, F0 has increased, because F0 is how much? F0 is that for one period, say 1 by t kind of thing, but your t is reduced, because this is your t and this is your t prime is reduced, so F0 is increased. So what is your bandwidth? 7F0 minus F0, 6F0, but in this case, your bandwidth is 7F0 prime minus F0 prime, so that means 6F0 prime. So but F0 prime is reduced, so your bandwidth in this case as time period is reduced, so your bandwidth is reduced. Okay, so that means you have higher bandwidth requirement, higher bandwidth with more cost. Anyway, now another trade-off is power versus bandwidth. Say, consider a system without coding operating at point D. Okay. Now, operating at required normalization. Okay. Say now we are talking about the power versus bandwidth. So consider the system without coding and operating at point D. Okay. So that means it is operating at point D, and the customer has no complaint about the quality of the data, because operating at point D means you are in 1 Mbps in 1 second you have only 1 bit of error. So voice quality is very good. Customer is happy about the voice quality, but your SNR requirement is 14. Okay. দেখুন আমি ক্লাসে আছি 15 মিনিট পর ফোন করছি। So now, but sometimes what happens that when you are operating at high power, so this type of that customer is facing reliability problem. Means what happened? Say when you are operating at say 8 SNR, means when you low power kind of thing, say you are generating the sinusoid in this way, fine. But sometimes what happened? But say in this case you are generating a big sinusoid. You are generating a big sinusoid. Sorry. What happened when sometimes due to saturation, say you cannot generate above this. So what you are getting something, then flipped, this is coming flipped. So this part you cannot generate. Means it is when the power is high, sometimes this quite happens. So that means your electronic circuitry, it cannot handle this one. Say in op-amp circuit, you know, that means say you are familiar with ideal op-amp. So when your supply voltage, the VCC and minus V is 3.3 volt, you cannot go most probably beyond 3.2 volt or something. Okay. So if your sinusoid, you are generating say some sinusoid which is something say 3.5 sinusoid, you cannot generate, or 3.4 sinusoid. Something you cannot generate. So that means high power means always this type. So in that case, say in your op-amp, say op-amp this supply is 3.3 volt, and say you have something like this, some output kind of some characteristics. So here your output, say this is your say 3.3 volt, this is minus 3.3 volt, and in this output that will be always flipped up to 3.2 volt, maybe minus 3.2. And if you generate, say if you have a requirement of 3.5 volt sinusoid, because in order to get that say this 14 dB SNR, then what will happen? From this point it will be flipped. Again it will come. This is that 3.2 volt line kind of. Okay. So now, so in that case, so that means you have to somehow reduce the power. Now, power should, then reliability issue will be reliability difficulty, or this type of nonlinearity maybe will be reduced. So what we will do, that means trade-off is by moving point D to E. Okay. So that means what you will do, from that uncoded one to you will move to the coded one here. So then your power level reduced, and suddenly you are moving to say this type of. Then you don't have the problem. Okay. Now, when you do this thing, that means you are coding, you are using the channel coding. This one, channel coding one means you are just again you are using more bandwidth. Now, for real-time communication, so that means you have to pack bits within that time frame. With that, I was explaining that within this time frame you have to do this one. You have to, for a real-time communication, you have to pack the extra number of bits inside this one. So suddenly your each waveform, each square wave will be switched, and suddenly each square wave switch means your fundamental frequency increase. Fundamental frequency increase means say 8f0 minus 7, say 9f0 minus f0, 7f0, so 6f0 is your bandwidth. So that will also increase. So that is bandwidth requirement. Now, so bandwidth, more bandwidth, you ask for more bandwidth from the government, means you have to pay. That's it. Now, if I don't go for a real-time communication, then people say, oh no, I don't have this. I need not pack the bits within this time. Then what will happen? So if you go by either for real-time communication, either you have to pack these extra bits, or if you say no, I will not increase the bandwidth by packing. I don't need a real-time communication, so I need not have any requirement of I have to deliver all the bits within this time. So then what will happen? If you don't change the bandwidth, then you have some extra time. You have some extra time. So extra time means you have more delay. Okay. So if either you have to give more bandwidth or you have to allow delay in the system. Okay. So now this is this is about power versus bandwidth. So what about the coding gain? Coding gain means say for the same probability of bit error, say earlier you are operating here, but on the uncoded region, and without losing the probability, means quality, voice quality, or without increasing the probability of bit error, you have moved to the coding this point, and this 9 minus 14, this is called, that is that 5 dB normalization, and this is called the coding gain. That means dB by N0 for uncoded minus dB by N0 coded. Okay, that dB by N0 for uncoded minus dB by N0 for coded in dB. Similarly, the data rate versus bandwidth, and another is the capacity versus bandwidth. This read these two on your own. It is simple. You can just follow this graph. You'll understand this thing. Okay, and there is some example. Please try to solve this example with some sort of interesting example, that coded versus uncoded performance. It has been a fantastic example. Please try to do that actually. Okay, please try to do by on your own, or maybe you can. Next is the linear block. Okay, I'll come to it. The linear block code is a class of parity check code that can be characterized by this NK notation described. That is, some say 6,31. 6, that in this bit is 3 bit, you will append extra 3 bits so that you will get a 6 bit kind of. Okay. So now this, and mainly we will talk about that restricted to binary code. We will talk about binary codes. Okay. So that means that k bit messages, it will give a 2 to the power k distinct message sequence. So that means say k bit means 3 bit, that means 0, 0 to 1, 1. So that means 2 to the power k distinct. Okay. Now that it is this one is called k-ting field. Okay. Sometimes Q fuel, tuple, whatever you like. Anyway, so sequence of k digits. Okay. Now this one I will convert this k bits, sequence of k bits, I will convert to sequence of n bits. Okay, so that is sequence of 3 bits, I will convert to sequence of 6 bits by adding some extra bits. Okay, so that means the encoding procedure will assign each of the 2 to the power k message, okay, 2 to the power k message, that is k to 1, k message, one of the 2 to the power n tuples. Okay. So that means what I like to say that means to say, just give an example. So that means I have some this one, then I will just convert it to this. Okay. Now you see how many? This is 8. This is 3. Sorry, this is 6. But it is 6 tuple. This is 3 tuple. This is 6 tuple. Okay. Now this is a subset of 2 to the power, means all possible 2 to the power 6 tuples. Okay. So that means what are the all possibles? All zeros to all ones. But I have not used all 2 to the power 6. I have used only 2 to the power 6 means how much? 64. But I have used only 8. Okay. So I have used 8 6-tuple sequence from the all possible 64 sequence. 64 6-tuple sequence. Okay. So now the block code represents a one-to-one assignment where the 2 to the power k message of k tuples are uniquely mapped to a new set of 2 to the power k code words of n tuples. This mapping can be, so that means what it is say, the code, this linear block code, actually it will do the mapping. 001 will be mapped to here, 100 will be mapped to here, 101 will be mapped to here, something like that. This map. Okay. Now this is called a linear block. So this is the code word and this is the message vector. Okay. Similarly at the receiver, from this one I will come back to this one. Okay. I will from this code word I will do certain operation and I will do the decoding and I will get this message. Now you try to understand, but I am not. So this is now this one for this uniquely mapped to a new set of 2 to the power k, means 8 forward of 6 tupules. The mapping can be accomplished via lookup table. That means what you can do, you can just keep this lookup table. Okay, if you try to understand. That means what I will do, I can store this. If I know the transmitter and receiver, it knows if I use only this one, and if I know that first row is for this vector, second row is for this vector, third. So see, this is not that 0 0 0 0 0 1 1 0. It is not. It is say 0. Then what is this? This is how much? 2 to the power 0, 2 to the power 1, 2 to the power 2. That means 4. Then this is 2. Then this is 4 plus 2, 6. Then this is 1. This is 4 plus 1, 5. This is 3. This is 7. Okay. This is not in a sequence. So it doesn't matter. So you can even put this one. It's the only thing is that say you can put 0 0 0 0 0 1 0 1 means 0 1 0. The same is you can change this order. Similarly, this order will get changed. And if you can only store, that means I know my message vector. If it is 0, then I will use this order. If I want, then I will use this one. And in this way, I will in that case, this sequence will also be changed in increasing order of the message vector. But thing is that this is one way. That means I will the encoder will store the decoder. Encoder will do this one, and the encoder will store this lookup table. Decoder will also store the lookup table. There is nothing great about it. Okay. Now this is called the accomplished by the mapping can be done by lookup table. Okay. And this mapping is for linear code. Please remember, for linear code. I was talking about linear. What is linearity? I will come to it. For linear code, this mapping transformation is also linear. I will come to it. Okay, please remember that here we are not talking block. It is any linear code means this transformation is linear. That is how what is the linearity. Now let us define the vector space. Okay, so vector space already you okay, maybe I will discuss this tomorrow, because vector space, vector subspace, I have to explain it. That means that it is a binary n tuples. That is the set of all binary n tuples. Bn is called a vector space over a binary field of 2 elements, 0 and 1. Please remember, binary field of 2 elements, 0 and 1. Okay, and the binary field has two operations, addition and multiplication, such that results of the all operations are same set of 2 elements. Okay. Now addition means say 0 means it is an XOR operation. 0 0 sorry 0 0 is 0, 0 1 is 1, 1 0 is 1, 1 1 is 0. That means 1 1 is 1 0. I will take the last bit. Similarly, multiplication means whenever either 0 is there means it will be 0, and if it is 1 into 1 1. The binary addition multiplication these two. Now so this is that means vector space means it is something like that. Say if it is a n tuple, say that means say 4 bits are there. That means 0 0 0 2 1 1. This is the combination. That is, if I have 0 0 0 1 2 all these things, this whole combination is called vector space. Okay, and that means it's a Vn. Okay, all, please remember, all binary n tuples, all 0 0 2 is 1, n tuples, 4 tuples, vector space, and over 2 elements, 0 and 1. So I have either 0 or 1 each element. Okay, and the field has two operations, that means addition and multiplication. And this we have already studied in linear algebra, maybe on a real vector space, complex vector space. We are talking about binary. Now vector subspace means this is a subset of this from, so that means 0, 0 to 2 you are 16. Now vector subspace means out of 16, say I may have chosen only 8 or only 7 or only 6. Then that combination is called the vector subspace. But thing is that the all 0 vector must be there. That means this is my in the subspace. So this is your vector space. Now vector subspace means you have to take the subset, but please remember this 0 must be there. Okay, it's all 0 vector must be there, and sum of any two vectors of S also should be in it. This is called closure property. That means if I choose 0, 0, 0, 1, then sum of these two, that means this is anywhere there. Okay. Now say I have a subspace 0, so that means must be there. Then I am saying that these things are also there. I am saying 1, 1, 1. I have to check whether it is a right subspace or not. No, because the summation of these two, that must be there. Summation of these two is 1, 1 is 0, 1, 0 is 1, 1, 0 is 1, 1, 0 is 1. Okay. Now summation of these two, 1, 0 is 1, 1, also this one. So this is the right subspace. Okay. So anyway, this is only 4 elements. This is a 4-dimensional subspace. Now we are talking about linear block codes. Please remember. Okay. So we'll take an example of, say, for example, the vector space V4 is totally populated by 2 to the power. So that I told that 0, 0, 0, 0, 1, 1. Say subspace that 0, 0, 0, 0, 1, 0, 1. They have taken a different one. So anyway, so let that I may take class tomorrow. That I will inform. Okay. Okay. Thank you very much. And hello. So when will be the exam? Hello, please be prepared. That means I can take exam in any day in this week. Okay. And please inform your other classmates that I can take exam any day in this week. Okay, thank you very much.